Hello, this is going to be a short video about how to calculate the feed-forward gains for your controller. So, where do the velocity feed-forwards, acceleration feed-forwards, and the jerk feed-forwards come from? Well, to do that, you either need to have a model of your system, the open loop transfer function, or the other method is to use trial and error, which is not so good. To start with, we're going to use an example of a motor, a simple motor that's got a gain, which is, say, millimeters or radians per second per percent output, and a bandwidth. And the bandwidth is determined by the mass and the amount of torque that the motor can produce. So down here we have the formula for the open loop transfer function. We have the velocity. This is the actual velocity, target velocity, the feed-forward gains of the controller, or open loop gains. Feed-forward gains are open loop gains. And this is the model for the motor. So down here, what we can see is that to have the actual velocity equal to the target velocity, what we need to have is the feed-forward terms of the controller be at times the model for the plant be equal to 1. You can see that from here. This term is 1, so that would mean the target and the actual velocities are the same. So for that to occur, what you must do is invert the plant model, or the open loop gains, or the open loop model for the motor. And what we've done here is shown the motor. This is the inverse of the open loop transfer function for the motor. And if we expand that out and collect on powers of s, we can see that there are two terms. So this is the velocity feed forward. This is the acceleration feed forward. So the calculations for the feed forwards for a motor are relatively simple, assuming that you have the bandwidth and the gain for the motor and load. Now, the bandwidth is the inverse of the time constant. So if you have the time constant for the motor and load, then you can just invert that to get alpha. A little bit more complicated example is doing this for a hydraulic actuator. And this is the velocity transfer function for a hydraulic actuator. There's a gain, which is basically the same gain as what you have for a motor. This is the velocity per percent output. But we have the natural frequency of the actuator and load, and the damping factor of the system. And the natural frequency, there are formulas for calculating the natural frequency, but you can also calculate this by system identification. Calculating out the damping factor is a little bit more difficult. You can assume 1/3, which is a pretty good approximation. It's usually between 0.2 and 0.4, but your transfer function will not be accurate. The procedure for calculating the feed forwards for the hydraulic actuator is basically the same. We have the same transfer function here, where we have the target velocity and actual velocity, and that they have to be equal. So the feed-forward gains times the actuator model, it have to be equal to 1. So therefore, the open loop gains have to be the inverse of the actuator model. So what we've done is we've taken the actuator model and we've inverted it here, and then we've expanded it out to get powers of s again. So now we have, since we have an extra s to the second power, we've got 3 terms here. This is the velocity feed forward. This is the same as what you had before with the motor. The velocity feed forward is always the inverse of your open loop gain. The acceleration feed forward, you can see, is different. It has the damping factor in it and the natural frequency. And then the jerk feed forward, and yes, there's a jerk feed forward, that is proportional to the 1 over the system gain, or the open loop gain, times the natural frequency squared. Now, like I said, there are formulas for calculating the natural frequency, but calculating the damping factor is difficult unless you have a system identification capability. But if you just put in 0.3 in here, or 0.33, you can get pretty close. So these are the formulas for the velocity feed forward, the acceleration feed forward, and the jerk feed forward. You can see that it's really pretty simple, and this makes a huge difference to how well you can track have the actual velocity track the target velocity. Now, all this assumes that you have a target generator that will generate a velocity and an acceleration and a jerk. And in our case, we use a fifth order motion profile so that these terms are all very smooth. Anyway, that concludes my video.